Brad, you can go ahead and begin anytime.
Okay. Well, welcome to the last seminar of the semester. Let me press continue first. And it's my pleasure to introduce Jerrold Acdan. He's going to be presenting the research that is making up his MS thesis on his way to his PhD thesis. And in a lot of ways, this is building capabilities for his follow-on PhD research. What he's going to be talking about is an extension of work that he did this past summer that was in support of the Lake Michigan Air Directors Consortium, which is the local agency that assists the 5-state area around the Great Lakes in managing their air quality. And he's looking at a particularly interesting application of satellite measurements and evaluating whether or not you can use these to assess ozone production regimes, in particular around the Lake Michigan region. So again, this is work that he led along. Tim Bertram and I were the PIs for the grant, but it was Jerrold and one of Tim's PhD students that led the research, and I will let Jerrold take it from here.
Great. Can you all hear me? Just making sure. I'm gonna start sharing my screen. And you all can see my presentation now that's pulled up. Great.
Yep, looks good.
Awesome. Thank you, Brad, for that introduction. So as you said, I'll be talking about highlights from my master's thesis, which is entitled Investigating Formaldehyde to Nitrogen Dioxide Ratios Using Satellite, In Situ, and Air Quality Modeling Data. But before I start talking specifically about these ratios, I'm going to start off with some background information. So the United States Environmental Protection Agency, or EPA, is tasked with addressing national environmental concerns, including toxic air pollution. And in particular, it regulates air pollution through enforcing the Clean Air Act of 1963 and its subsequent amendments. So the EPA sets national ambient air quality standards for 6 criteria air pollutants. And these standards are atmospheric abundance levels above which concentrations of air pollutants are known to negatively impact human health and the environment. And one of these pollutants, and in particular relevant to my research, is ground level ozone. So ground level ozone is a gaseous molecule, and it consists of 3 oxygen molecules. If you want to see what they kind of look like, that's what these little icons are up here. 3 little blobs mushed together that look like ozone. And in particular, ozone is regulated because breathing it in can cause acute respiratory problems like coughing or wheezing. It can worsen chronic respiratory conditions like asthma, and it can even lead to premature death. And additionally, ozone also is damaging to plants and can cause agricultural crop failure. So there's a lot of motivation to regulate ozone concentrations in our atmosphere because of these impacts. So the ozone NACs, or the air quality standards, are currently set at an MDA8, or daily maximum 8-hour average value of 70 parts per billion by volume, or ppbv. And counties in the United States where ozone levels have been observed to exceed this value are deemed ozone non-attainment areas. And they are required by the Clean Air Act to develop plans to address the ozone problem. So as seen on this map on the right, which I adapted from the US EPA, ozone NAAs include counties surrounding the Lake Michigan region, as seen here, where the problems are deemed marginal. In particular, the Chicago metropolitan area, as well as, it's harder to see, but counties along the eastern coast of Wisconsin. And this box highlights the Lake Michigan region that forms a large part of the study area for my work. So in order to address ozone problems, it's important to know where it comes from. And ozone is actually a secondary pollutant, meaning that it's not directly emitted into the atmosphere from a specific source. It is actually formed in a complex series of photochemical reactions involving nitrogen oxides, or NOx, and volatile organic compounds, or VOCs, such as formaldehyde. So NOx can come from fossil fuel combustion emissions from cars, trucks, and power plants, while VOC sources can come from many different things, including industrial emissions, household products like paint and aerosols, as well as natural or biogenic emissions from plants. So for example, if NOx emissions from a factory mix with regional emissions of VOCs from plants in surrounding rural areas, and this mixture occurs in the presence of sunlight, ozone can be formed. However, decreasing ozone concentrations isn't simple because ozone production depends non-linearly on NOx and VOC concentrations. This can be seen in a diagram called an ozone isopleth, which is shown here on the right. In such a diagram, on the x-axis, we see emissions of VOCs, while on the y-axis, we have emissions of NOx. While the color shading indicates ozone concentrations depending on where you are in your mixture of emissions of VOCs and NOx. And when I say that ozone production depends non-linearly on NOx and VOC concentrations, I mean that if you decrease NOx concentrations, it could actually lead to increases in ozone as indicated by this purple arrow. Or here, if you decrease VOC concentrations, it can actually lead to increases in ozone, even though you're decreasing one of the precursor species. So despite this complication, ozone production can be thought of as occurring in two regimes. In the NOx sensitive regime, which would be right here on this part of the graph, increasing NOx levels will actually increase ozone concentrations, while decreasing NOx will decrease ozone concentrations. And similarly, for the VOC sensitive ozone production regime, if you increase VOCs, that results in more ozone, while decreasing it will result in less ozone. So one of the ways that these regimes can be identified is through the use of the ratio of formaldehyde concentrations, which is a VOC, to nitrogen dioxide concentrations, which is a component of NOx. And I'll refer to this ratio from here on out as the FNR. And previous studies have shown that higher FNR values, which means more formaldehyde and less NO2, are correlated to NOx sensitive ozone production, while lower FNR values, which corresponds to less formaldehyde and more NO2, are correlated to VOC sensitive ozone production. So this leads to the question of what FNR values correspond to the two different ozone production regimes. And early modeling studies incorporated modeled boundary layer conditions of formaldehyde and nitrogen dioxide to determine the threshold values. And generally, they found that an FNR value of around 1 was found to be the transition between the regimes. Subsequent research after those early modeling studies sought to apply this concept to satellite data because satellite data often gives a better spatial coverage than ground data can. For example, a study by Duncan et al. Published in 2010, which I'll refer to as D10 from here on out, determined thresholds via modeling, and then applied these thresholds to satellite data from the Aura ozone monitoring instrument. However, concerns have arisen around this approach because modeling primarily relies on boundary layer concentrations, and the boundary layer is often found in altitudes from 0.2 to 2 kilometers. And so it's closer to the surface. Satellite data, on the other hand, retrieves full tropospheric column concentrations. And the troposphere often goes from 9 to 17 kilometers high up into the atmosphere. And so there's a discrepancy between surface and the column. And so in other words, if we calculate the FNR ratios in the planetary boundary layer versus the troposphere, they may be very different. A more recent study by Jin et al. That was published in 2020 used the same satellite data source as Duncan et al., but they determined their threshold values differently by connecting them to satellite FNRs, connecting satellite FNRs to high ozone event probabilities, which were calculated from in situ data. And so, as we can see in the table below, despite using the same satellite data source, there are large discrepancy in the threshold values found by these studies. In particular, the J20 thresholds for VOC sensitivity is 3 times larger, and for NOx sensitivity is 2 times larger than the thresholds that were found by Duncan et al. And so this, with all of this stuff in mind, it led me to 2 main research questions, which are: 1, which FNR threshold values for NOx sensitive versus VOC sensitive ozone production should be applied to satellite-based FNRs? And the second is, how do satellite-based ratios compare to the ground-based ratios? And so I'll start with addressing the first question. So the data I used to address this first question comes from the Sentinel-5 precursor satellites tropospheric monitoring instrument, which provides retrievals of NO2 and formaldehyde at similar signal to noise ratios to the Aura-OMI instrument that the previous studies I referenced used, but it has a much better spatial resolution. And to calculate these satellite FNRs, I first applied quality control and detection limit filters. And then I composited these filtered data, NO2 and formaldehyde data, onto a 12 kilometer by 12 kilometer Lambert conformal conic grid. And I created monthly composites for the ozone seasons of 2018 and 2019. And I also created composites for ozone exceedance days where I only composited satellite data where on days where a ground instrument measured an MD8 ozone value greater than 70 parts per billion. And finally, I calculated the FNR by dividing the composites of formaldehyde and NO2. So here's a couple images of July 2018 NO2 and July 2018 formaldehyde. These images show the extent of the grid onto which I composited the satellite data. And for the rest of the results that I'll be showing you, I'm going to be focusing on this red domain again. This domain indicated by the red box, which encompasses the Lake Michigan region. So as I mentioned earlier, I created composites for the 2018 and 2019 ozone seasons. You may notice that the months slightly differ, and that's because tropomi data wasn't available in May 2018, but it did become available in June 2018, which is why there's a month different. And so here's what the results look like for formaldehyde and NO2 when we zoom in to the Lake Michigan region. In the left column is July 2018, and in this middle column is July 2019. And then in this last column is the difference between the two. And so, and the difference I took as 2019 minus 2018. And so we can see here that formaldehyde is more uniformly distributed, but it's noisier than NO2. So if we look here in the formaldehyde composites, there's no clear hotspots of where formaldehyde might be coming from. It's more constant throughout the, not constant, but yeah, there are no hotspots in the domain. And when I say that formaldehyde is noisier, if you subtract the 2 months, you can see that there isn't a clear pattern in the difference between the 2 years. For NO2, there is a clear hotspot in this domain, and that is that the highest NO2 levels are seen in the Chicago metropolitan area, here and here. There are annual changes in NO2 that are evident in the Chicago area, as well as over Lake Michigan. So we can see here that it looks like in 2019, there were less, the atmospheric levels of NO2 were slightly less than in 2018, while over the lake, it looks like NO2 was higher. And these differences suggest possibly changes in emissions, but more likely just changes in the transport of NO2 after being emitted into the atmosphere. Okay, so if we divide those two composites of formaldehyde and NO2, we get the ratio. And here we see on the left column, again, July 2018, in the middle, July 2019, and the difference. And from these composites, we see that the highest FNR values occur on the eastern side of Lake Michigan. And that means that the ozone production in those regions is likely more NOx sensitive, while the lowest FNR values are found in the Chicago metropolitan area, again, because that's where most of the NO2 is being emitted. And because these values are lower, that means the ozone production in this region is likely more VOC sensitive. And if we look at the difference here between the 2 years, it's pretty noisy too. And that tells us it looks much like the one for formaldehyde rather than NO2, which tells us that these differences between the years are more likely driven by differences in formaldehyde rather than NO2 necessarily. Okay, so in addition to creating the monthly composites, I also said earlier that I created ozone exceedance composites, which led to this additional question of how do FNR values change between an ozone season composite versus an ozone exceedance day composite. And when I say ozone season composite, I'm referring to the average of days within the ozone seasons of 2018 and 2019, which I created by taking the weighted average of the formaldehyde monthly composites and dividing them by the weighted average of the NO2 monthly composites. And this is in contrast to an ozone exceedance day composite, which includes only satellite data for days where a ground monitor within my domain of interest measures an ozone concentration greater than the ozone max value of 70 parts per billion. And so, yeah, for ozone exceedance day composites, I would pick a region of interest. So for example, I'm interested in Chicago, and I'm only compositing satellite data for days when Chicago experiences an ozone exceedance day. So this is what the composites look like. On the left is the ozone season composite, and in the middle is a composite of satellite data for Chicago exceedance days. And in general, we see that FNR values increase during exceedance events because this difference I took as the exceedance composite minus the season. And as a result of these higher FNR values, we see that during exceedance days regionally, there's more NOx sensitivity with regards to ozone production. But a question remains, why are there differences and what leads to these differences? So if we look at formaldehyde and NO2 individually, we see that the regional formaldehyde levels are are greater during Chicago exceedance days than during the typical ozone season, which means that these regional differences in formaldehyde levels cause changes in ozone production, as opposed to NO2, which we see the differences are less noticeable. And after running some statistical tests between these two composites, it is shown that formaldehyde is statistically significantly different during exceedance days than the ozone season. And so we can attribute the differences in FNR values to differences in formaldehyde largely. Okay, so what do these differences in FNR values between the ozone season and ozone exceedance days imply for ozone production? Well, that depends on which thresholds we apply to the satellite FNRs. As we can see here, if we're using the Duncan et al. Thresholds, there's essentially no difference in ozone production regimes when we look at the ozone season versus Chicago exceedance days. However, if we use the Jin et al. 2020 thresholds, we see a much different story. So while the Chicago metropolitan area remains VOC sensitive, here in gray, during Chicago exceedance days, there's a big reduction in the transition zone, which is in yellow, during exceedance days, especially along the eastern coast of Wisconsin, where the ozone production becomes more NOx sensitive. So the fact that this analysis shows that using the J20 thresholds reveals much more information suggests an answer to my first research question, which is that it appears that the Jin et al. FNR threshold values probably should be applied to the satellite data as opposed to the Duncan et al. Thresholds. So now that we have an answer to the first research question, I'm going to move on to the second research question, which is how do satellite-based FNRs compare to ground-based FNRs? So to address this question, I used ground data from EPA photochemical assessment monitoring stations. And in particular, I focused on 4 sites, including 4 sites in Indiana, Illinois, Michigan, and Missouri. I'm going to be showing you specifically the results for the Schiller Park EPA PAM station because it's around Chicago. And at these stations, there were concurrent measurements of formaldehyde and NO2. Some of the formaldehyde was either daily measurements or 8-hourly measurements, while the NO2 data were all hourly measurements. So to calculate ground FNRs, I calculated daily FNRs by dividing the daily formaldehyde and daily NO2, and then I averaged these daily FNRs to get a composited monthly value. And then finally, I located the closest tropomi composite grid box that the EPA PAM sites fall into in order to extract the satellite composite ratio for comparison. So here are the results for Schiller Park, Illinois for 2018 and 2019. The pinkish dots represent the satellite FNRs, while the black dots represent the ground-based FNRs. And it is pretty clear that the satellite FNRs are greater than the ground FNRs for all months. And these same results we're seen for all the study sites, even though I'm not showing them here, they all showed similar patterns in which the satellite FNRs are greater than the ground FNRs. And so that answers the second question, my second research question. And so that led me to one more additional research question, which is what accounts for these differences between satellite-based and ground-based FNRs? So I have 2 hypotheses, and my first one, hypothesis A, is that daily averaging formaldehyde and NO2 ground data from the EPA PAM sites will impact FNR values. And then my second hypothesis is that the vertical profiles of formaldehyde and nitrogen dioxide are different, which leads to column ratios, which a satellite would measure, would lead that to a different one than what the surface ratio is, which is what a ground instrument would measure. So to test hypothesis A, I used data collected during the Lake Michigan Ozone Study 2017 field campaign. And the reason I'm using these data is because during the campaign, the US EPA took in situ measurements of formaldehyde and NO2 at a high temporal resolution of 1 minute at a site called Spaceport Sheboygan, which can be seen here on the map. And it falls into my study area of my work. And because of the high temporal resolution of the data, I was able to average the data into different block intervals. For example, 1 minute versus 5 minute averages versus hourly and daily. And therefore I was able to see how that affects the calculated FNRs. So here's what that looks like. In this graph, on the y-axis is over time, and on the x-axis shows the date, and the y-axis shows the FNR value. And as we can see, the values change over time, and depending on how much I average the data before I calculate the FNR value, that results in different FNR values. So for example, here on this plot, the green lines indicate the raw data ratios of 1 minute versus the black shows when I average the data into 5 minute intervals, what the ratios look like, and then hourlies in blue and dailies in red. And as we can see, as the averaging interval increases, the calculated FNR value decreases. And this is important because this can lead to differing interpretations of ozone production sensitivity. So for example, if I take this point here, the daily average of the data and the corresponding FNR would read that on this date at this time, ozone production is VOC sensitive. However, if we looked at the data averaged into smaller blocks, we see that the hourly, the 5 minute, and the raw 1 minute data all indicate NOx sensitive ozone production. So this reveals a limitation of the EPA PAMS data that I was using, which often only had daily formaldehyde measurements at different sites. Okay, so moving on to how I tested hypothesis B, which was the vertical profile differences between formaldehyde and NO2. I used air quality modeling data that came from high resolution community multi-scale air quality CMAQ modeling system simulations that were conducted by my advisor and other colleagues. And in particular, I looked at vertical profiles of formaldehyde and NO2, and I analyzed them as curtain plots over the grid box containing Spaceport Sheboygan. And then I also compared the modeled NO2 to some in situ scientific aviation flight observations of NO2. So here's what the curtain plots look like, which show what the vertical profiles of NO2 and formaldehyde look like over Spaceport Sheboygan throughout time during the modeling timeframe. And it is clear, for example, in this red box that formaldehyde often extends farther up into the atmosphere. And so that could lead to different ratio values than what is seen at the surface versus at a full column, which a satellite would see. And so while this is an interesting finding, how do we know that this is real, considering that these currents are derived from model simulations? And in particular, if we zoom in into the NO2 plot, what are these like weird looking NO2 features that are separated from the surface? Like, are these features actually real? So unfortunately, there were no in situ formaldehyde vertical profiles measured during the field campaign, but we do have in situ observations of NO2, which I will show you comparison. So I'm focusing on, sorry, let me go back. I'm focusing on here on this plume here on this specific day on which we had a flight of measuring in situ NO2. So on June 2nd, 2017, this was the flight track. And on that day, as the aircraft that was measuring NO2 in the atmosphere was ending its flight, it made some spirals above Spaceport Sheboygan. So it made an upward spiral measuring NO2 as it went upward, which you can see here in the black. And it also made a downward spiral as it went back down towards the ground, which is on the right side. And on these plots, we can see that the in situ aircraft instruments did measure these lofted NO2 features. And in red, we can see what the model predicted or simulated. And as we can see, even though the model may be underestimating these lofted NO2 features, the fact that the model sees these lifted NO2 features and that we can see that these NO2 features exist from the in situ flight craft data, that gives us some confidence in our model results. So now that we know that these lofted NO2 features are real, where do they come from? And so it turns out that down the road from the Spaceport Sheboygan ground site is the Edgewater coal power plant in Sheboygan, Wisconsin. And as seen in this loop from the high resolution CMAC modeling simulations, we can see that wind is pushing the coal power plant NO2 emissions over Spaceport Sheboygan, which ultimately affects ozone production in the area. And to me personally, this loop is actually pretty exciting because it demonstrates that modeling is able to resolve the emissions and transport of air pollutants from individual point sources like the Edgewater coal power plant. All right, so now I'm going to summarize some of the things that I've been talking about today in relation to the research questions I asked. So regarding which threshold value should be applied to satellite FNRs, it appears that satellite-based and ground-based FNRs require different thresholds for determining ozone production regimes. And in particular, the Jin et al. 2020 thresholds appear to be more accurate than the Duncan et al. 2010 thresholds for satellite-based FNRs. From my second question, how do the satellite and ground FNRs compare? The satellite FNR values were always larger than the ground FNR values at the EPA PAM sites that I studied. And these differences can be partially explained by the daily averaging of ground data, which leads to decreased FNR values, as well as differences in the vertical profiles of formaldehyde and NO2 that lead to a further disconnect between the surface FNR and a column FNR. And before I finish, I wanted to quickly mention that where I'm going for my PhD level work. I'm switching geographic locations to the New York City metropolitan area, which also has coastal ozone issues, as you can see here in this map and in this red box. This work will be a follow-up to the Long Island Sound Tropospheric Ozone Study 2018 field campaign. And so throughout my master's level work, I've been analyzing air quality simulation output that have been conducted by others. But for my PhD level work, I will become a modeler myself, and I will be conducting high resolution CMAC air quality simulations in order to investigate the ozone problems in the Long Island Sound region, which is pretty exciting. So with that, I just want to give some thanks, in particular to my master's committee, including my advisor, Brad Pierce, and professors Tim Bertram and Tracy Holloway. I'd also like to thank our collaborators at the Lake Michigan Air Directors Consortium and the Wisconsin Department of Natural Resources, and also our data providers from the European Space Agency, Scientific Aviation, and the US Environmental Protection Agency. And with that, I'll take any questions anyone may have. Thanks for listening.
Thanks, Jerrold. I'll note that for your Long Island Sound study, you've got a pending finesse proposal at NASA to pursue that research, and that you've also been invited to go to the ACOM modeling group at NCAR for a summer internship there to work with the excellent modelers that are in that area and measurement people as well. So any questions for Jerrold? John?
You mean me, Brad?
Yes.
Yeah. Jerrold, excellent talk. I didn't know anything about this subject until I heard about it from you. So this was really exciting. My basic question is there anything in the synoptic meteorology, not just the lake breeze, which was obvious in your simulation at the end, but is there anything in the synoptic meteorology that punctuates some of the productions or changes in concentration of either of the two species that make the ozone production sensitive?
Yeah, I would say yes. Although, yes, you can see the lake breeze here, also the general like wind patterns of like the direction in which the wind moves over the Lake Michigan region also moves like NO2, for example.
Mm-hmm.
Like it'll move NO2 that's being emitted from Chicago over along the eastern coast of Wisconsin, which plays a role into like the ozone problems along the coast.
Mm-hmm.
And the same thing goes for like regional emissions of VOCs. So like a lot of rural areas emit. Sorry, let me go back to the slide. Way back. Yeah, so like a lot of rural areas will have a lot of plants that emit VOCs, and so when the synoptic weather patterns like push the VOCs from the more rural areas into more urban areas where NOx is being emitted, that can lead to the mixture that results in ozone. So that's what I would say. Yeah.
And if I could follow up, what about the conditions that modify the release of VOCs by rural or agricultural areas? Are they synoptically related? So in other words, drying or heating or any changes in temperature, moisture, or various characteristics like that, do they have anything to do with the volume of VOCs that might be emitted?
Yeah, I mean, I'm not sure about all the factors, but I know definitely the temperature is very important. So when it's warmer outside, more VOCs are released by plants.
Okay.
So that's why during ozone exceedance days, it's particularly hot because there's a lot of VOCs in the air, usually from regional rural areas.
Yeah, and there's also a kind of more difficult for the air in the boundary layer to get mixed out on certain of those hot days, because sometimes there actually is an inversion. We had that in the famous July of 1998. Was it? I think the really big heat wave in Chicago area was like that. It's a very strange synoptic environment. Thanks.
Jonathan, I'll add that soil moisture actually has a big impact on VOC emissions as well. So the meteorology and the hydrology impact all these emissions.
Yeah, very interesting. Thanks.
Grant, you have a question?
Yeah, I do. So first of all, I enjoyed the talk. It's very interesting to learn about this. You talked at the beginning about the satellite-derived FNR, and I assume that the satellite is looking at column VOC versus column NOx or NO2. How safe is the assumption that the two are co-located vertically in the column so that you're getting a ratio that actually is relevant to production?
That's a good question. I actually don't know the answer to that, but they're measured from the same instrument. So I'm assuming they would be co-located. I'm not sure if Brad would have a better
So they're co-located in space, but I think what Grant's saying is, are there differences in the vertical distribution of those two species? which was one of your hypothesis questions, right?
Yeah, if that's what you were asking, then you know, like our modeling shows this, that there are vertical differences. Yeah, I'm not sure I understand your question 100%.
So maybe let me phrase it another way. You showed that you could have a plume of NOx at a specific level above the surface, and that plume might be at, say, 1 kilometer altitude, and you might have then the concentration of VOC in the lower boundary, in the boundary layer or something, so they're not even in the same place vertically and not interacting with each other. And so that would change the meaning of that ratio in terms of what the satellite is observing in the column.
Yeah, that's actually a very good point that I didn't think of. So that is I guess that would be a limitation to using satellite ratios because of what you were saying.
And maybe a kind of a correlated question would then be whether that's something that anybody is directly investigating by looking at in situ measurements of the profiles as compared with the satellite observations.
I'm not aware of any research that's currently doing that. I think maybe because in situ profiles of like formaldehyde aren't necessarily like done that often. I'm not sure. Yeah.
So Grant, there was a NASA funded their first venture class suborbital mission was called Discover AQ, and it was a 5-year mission that flew over all sorts of metropolitan areas, addressing exactly the question you asked: is how does column concentrations compare with surface, and provided in situ profiling of a wide range of species to try and address that. So for LMOS, we only had NO2. For Discover AQ, they had NO2 and formaldehyde, and we're really able to drill down on that specific question.
Thank you.
I think that Tracy had a question.
Yeah, Jerrold, I just wanted to say really, really nice, nice talk. I love this topic. Actually, Xiaoming Jin, who developed the second set of the ratios, started that work here at Wisconsin when she was a master's student with me a number of years ago. And it's so exciting to see your work following up on that. So I have a lot of questions I could ask, but I just want to start with one that's kind of limited here to one kind of basic, which is about the resolution that you're using. Because I saw that you were allocating the satellite data to the 12 kilometer by 12 kilometer grid. And so I thought that might be because you were later going to compare with a model at 12 kilometers by 12 kilometers. But then your model is higher resolution. And so I guess I was curious, why not use higher resolution satellite data instead of going to the coarser resolution? Why not get as much information as you can out of those high resolution tropomi retrievals?
Yeah, that's a good question. So I'm gonna move up. I don't have an extra slide specifically for the resolution. But the reason I used a 12 by 12 kilometer grid is because when I used a 4 by 4 kilometer grid, which was smaller, it resulted in very noisy like results. And so we decided to do monthly composites onto a larger domain because it allowed us to get more full coverage of the domain, and also we can like identify and analyze general spatial patterns. And so that's the reason why I didn't use a smaller grid.
Okay.
Yeah, we tried the 4 kilometer one, and it was too noisy.
Yeah, no, that makes total sense. And I think there's so many exciting directions this work can go. It'll be great to hear how it's going to develop through your PhD.
Thank you.
We're looking forward to tempo data, which has a better signal to noise ratio than either OMI or tropomi, and that for formaldehyde, so that we don't have to average so much to knock down that noise. There's a question in the chat from Brooke. Similar to John's question, do particular synoptic conditions influence or exacerbate the differences between satellite versus ground-based measurements?
Oh, that's a good question too. That's not something that I've looked at. But I mean, I don't. Yeah, I'm not sure. Like, if there's a lot of clouds, for example, that would affect satellite instruments retrievals, and you would get less information compared to something that would be measured on the ground, which wouldn't be affected by clouds if clouds are considered synoptic in nature or mesoscale. I'm not sure. But other than that, that's a good question. I haven't thought about that either.
I think we found that I think you talked about trying to do a ozone exceedance day composite for the PAMS data, right? But I'm not sure that we had enough PAMS data to do that, maybe.
Yeah, there wasn't enough data.
Are there any other questions? Let me see if anyone's got their hand raised virtually. I don't see it. No, I don't see any other questions. If there aren't any more questions, then let's thank our speaker, Jerrold Acdan. And thank you very much.
Great job. Thank you.